everyone, welcome to today's explainer. Look, if you've ever written code for a GPU, you already know it's crazy fast. But have you ever actually stopped to think about the physical wizardry making that speed happen? Today, we're going to demystify the magic behind GPU computing. We're going to completely bridge that gap between the code you type on your screen and the physical silicon chip that's actually processing it. No magic wands here, just mapping your software blueprint straight to the machine. So let's just dive right into the core dilemma here. When you write software, you're using these clean, beautiful abstractions, right? You tell the system to spin up grids and blocks of threads. But the hardware doesn't actually speak that language. At the physical level, it's operating with streaming multiprocessors, partitions, and cores. So how exactly do they connect? How does your abstract code turn into actual electricity firing across a chip? To figure that out, here's our roadmap for today. We'll look at the software blueprint, check out the hardware engine, discover the missing link called warps, run a step-by-step kernel launch, and then pull back for the big picture. All right, part one, let's look at that software blueprint. First up, we have the grid. When you tell a GPU to do a specific job, say adding two massive arrays together, you launch what's called a kernel. Now, a grid is literally the entire wave of work created by that single kernel launch. It's the macro-level task you're handing off to the GPU. You can kind of think of it as the master blueprint for your specific job. Now, inside that master grid, we've got blocks. A block is essentially a team of cooperating threads. And the really cool thing about a block is that all the threads inside it are guaranteed to run on the exact same piece of hardware. Because they're physically close together, they can easily synchronize their work and share incredibly fast on-chip memory with each other. And finally, zooming all the way down, we find the thread. The thread is the absolute smallest, most fundamental unit of execution. Typically, a single thread handles just one discrete piece of data. That could be calculating the color of a single pixel on a screen, or just adding together one element in that array example we talked about. So to sum it up, your software blueprint is perfectly nested. You launch one kernel, which creates one grid. That grid is made of multiple blocks, and those blocks contain multiple threads. It's a super clean, logical hierarchy. Okay, so we've got our code blueprint ready and perfectly organized, but what does the physical chip actually look like? What machinery is actually waiting to execute all this? That brings us to part two, the hardware engine itself. And this right here illustrates the exact divide we're exploring today. On the left, you've got your abstract programmer's view, grids, blocks, threads. But over on the right, you have the physical silicon reality, the GPU chip, SMs, partitions, and cores. Now, the absolute star of the hardware show is the Streaming Multiprocessor, or SM for short. Honestly, you can just think of an SM as a mini GPU factory. A modern GPU is really just a massive chip containing a whole bunch of these identical SM factories. And each SM comes fully equipped with its own register files, shared memory, and a massive pool of execution cores. And just like our software, the physical chip scales down structurally too. The whole GPU chip has many SM factories. Inside, modern SMs are actually split into smaller subsections called SM partitions, and each of those gets its own scheduler. Zoom all the way down into those partitions, and boom, you find the physical cores. These are the actual hardware units doing the heavy math lifting, like CUDA cores or tensor cores. Which leads us to part three, warps, the missing link. So what is the missing link? It's something called a warp. Now, you won't explicitly write a warp in your standard code, but it is exactly how the hardware manages your threads. A warp is just a group of 32 consecutive threads from a block that the hardware bundles together. The GPU then takes this bundle and executes it in lockstep, meaning all 32 threads execute the exact same instruction at the exact same time, just on different pieces of data. And here is the definitive mapping matrix you absolutely need to know. Your grid gets distributed across the entire GPU. Your blocks, those are assigned entirely to one SM. Inside that SM, threads are bundled into warps, handled by SM partitions. And finally, the individual threads run directly on the physical cores. I really want you to notice this specific number, 32. Because the hardware forces threads into bundles of exactly 32. Understanding this limit is absolutely crucial. See, if threads inside a warp suddenly disagree on, say, an if-else statement, they can't just split up. The hardware has to execute one path while literally pausing the others. That's called warp divergence, and keeping that number 32 in mind is how you avoid it. Okay, let's move to part 4 and run a step-by-step kernel launch. Let's see what happens the exact millisecond you hit run. Step 1, your computer's driver enqueues your software grid to the GPU. Step 2, the hardware looks at all your blocks and distributes them across the available SM factories. You don't control this part, the hardware does it for you. Step 3, inside the SM, your threads get sliced into those warps of 32. And finally, step 4, the SM partition schedulers look for warps that are ready to go, and they fire those instructions directly into the execution cores. Now, you might be wondering, what if we're training some massive model across multiple GPUs? Well, even if you scale up using data parallelism across devices, the rules literally don't change. You partition your data, each GPU gets a chunk, and inside each individual GPU, that exact same grid-to-core hierarchy we just simulated remains totally identical.
All right, part 5. Let's step back for the big picture.
If you take away only one single thing from this explainer, please let it be this foundational quote. I write grids, blocks, and threads, but the hardware runs SMs, partitions, warps, and cores. Keeping that clean separation in your head is seriously your superpower here. When your profiler complains that your occupancy is low, you'll know it just means your SMs are starved for warps. When it screams about divergence, you'll know your warps are taking different paths on the physical cores. So, now that you actually understand the physical silicon reality sitting right beneath your software abstractions, how are you going to optimize your next piece of code to perfectly feed this hardware engine? Are you going to adjust your block sizes to maximize those warps of 32? Maybe rethink your shared memory so more blocks can fit onto a single SM. The software blueprint is completely in your hands. But now you know exactly how the machine builds it.